This series of hormone deals with GPAT questions and answers with explanations. This is the part 2 of the same. This part consists of questions asked in GPAT 2020. First question of this part is: which of the following is not a fundamental factor considered for selection of a location for the construction of pharmaceutical or chemical plant? 4 options are given: soil, market for products, labor supply, raw materials. Out of which soil is the right answer. There is no need to consider the type and quality of soil while selecting the location for a pharmaceutical or chemical plant. There is no relationship between the product being manufactured in that plant and the soil of that location. But the pharmaceutical operations are directly related to market for the product. We have to consider whether the product being manufactured there can be sold in the market of the nearby locations. If we construct a plant where adequate labor supply is not available, we cannot do manufacturing operations in that plant. If we construct the plant where raw materials are not available, the operations are affected. The raw material should be available easily and in a cost-effective manner. So, we have to consider market for products, labor supply, raw materials, etc. while selecting the location of a pharmaceutical plant. But no need to consider the nature and type of soil at that location. Next question asked in GPAT 2020 is: the following gram-positive bacteria species is positive for the coagulase test. Out of the 4 options, Staphylococcus aureus gives positive coagulase test. Now we will move on to the details of coagulase test. The coagulase is an enzyme which converts fibrinogen to fibrin. This fibrin helps for clot formation. Certain bacteria can produce coagulase enzyme. So, if we want to know whether a bacteria produces coagulase enzyme, we can do coagulase test. That is, coagulase test is a test used for detecting the ability of a bacteria to produce clot in blood plasma. Bacteria in Staphylococcus genus are classified into 2 groups. The first group can produce coagulase enzyme, but the second group cannot produce coagulase enzyme. 2 microorganisms comes under first group: Staphylococcus aureus and Staphylococcus intermedius. These 2 microorganisms can produce coagulase enzyme so that they will give positive coagulase test. All other species which comes under Staphylococcus genus cannot produce coagulase enzyme, so that they will give negative coagulase test. Only Staphylococcus aureus and Staphylococcus intermedius gives positive coagulase test, and all other Staphylococcus species give negative coagulase test. You can see that here the species Staphylococcus epidermidis, Staphylococcus saprophyticus and Staphylococcus lactis cannot produce coagulase enzyme, and they give negative coagulase test. Next question is, the temperature dependence and theory of viscosity is expressed by the following equation. 4 options are given: Stern-Volmer equation, Arrhenius equation, Higuchi equation and Gibbs equation, out of which Arrhenius equation of chemical kinetics is the right answer. This equation can relate the temperature and viscosity. Let's see the basic Arrhenius equation. K is equal to A into e raised to minus EA by RT, where K is the rate constant, A is the pre-exponential factor, EA is the activation energy, R is the universal gas constant, T is the absolute temperature in Kelvin. This basic Arrhenius equation can be applied to relate the temperature and viscosity. Activation energy of a chemical reaction can be expressed in 2 methods. First one is in terms of energy per mole. Second one is in terms of energy per reactant molecule. If we express the activation energy in terms of energy per mole, we can use universal gas constant in the Arrhenius equation. But when we express the activation energy in terms of energy per reactant molecule, the universal gas constant should be replaced with Boltzmann constant. I repeat, if we express activation energy in terms of energy per mole, we can use universal gas constant in the Arrhenius equation. If we express the activation energy in terms of energy per reactant molecule, this is not energy per mole, but it is energy per reactant molecule. If we express the activation energy in terms of energy per reactant molecule, we should use Boltzmann constant in the Arrhenius equation. That is, we have to replace the universal gas constant with the Boltzmann's constant. What are the applications of Arrhenius equation? We can apply Arrhenius equation in 3 fields. First one is to show the temperature dependence of chemical reaction rate. Second one is to determine the rate of chemical reactions. Third one is to relate the viscosity and temperature. That is, to relate the temperature dependence of viscosity of a given fluid. You can see Arrhenius plot here. On y-axis, you can see log K. We know K is the reaction rate constant. Log of K can be plotted on y-axis. And on x-axis, you can see inverse of temperature, that is 1 by T, can be taken in the x-axis. When we plot this, a straight line can be obtained. The slope of that straight line is equal to minus EA by R, from which we can calculate activation energy EA. The y-intercept of the straight line is log A. I repeat, slope of the Arrhenius plot is equal to minus EA by R, and y-intercept of Arrhenius plot is equal to log A. We have seen that A is pre-exponential factor, which is otherwise known as frequency factor. This frequency factor deals with the collision between molecules. Actually, it is the frequency of collisions between molecules which have sufficient energy to start a chemical reaction. And in this question, we have seen some other options also. Along with the Arrhenius equation, we have seen the names of some other equations which are also explained here. The first equation was Stern-Volmer equation. You can see the equation here. This equation is related to fluorescent spectroscopy. As it is related to fluorescence, I will explain about fluorescence first. Some molecules absorb light. They can absorb visible light or ultraviolet light. By that absorption, they absorb energy. This energy is utilized for excitation. That is, the molecule will be excited from ground state to an excited state, and later they will release energy. That is, the excited state will release energy. They release energy in the form of radiation. That radiation may be a visible light or may be a near infrared light. The emitted light is known as fluorescence. By absorption of light, the ground state can be excited into two forms, either a singlet form or a triplet form. If a molecule is excited to a singlet form, that singlet form can release energy in the form of radiation. That radiation can be called as fluorescence. Some molecules are excited to triplet state. That will also release energy. If it is a triplet state, the released radiation can be called as phosphorescence. Actually, the radiation absorbed are so intense. That is, the absorbed wavelength is very high when compared with the emitted wavelength. When we compare the wavelength maxima, that is lambda max of absorbed light and that of the emitted light, we can see a difference. That difference can be called as Stokes shift. That is, Stokes shift is the difference between the lambda max of the absorbed light and the lambda max of the emitted light. And this term is related to fluorescence and phosphorescence. A term related to fluorescence is quencher. Quencher means a molecule that can absorb the energy which is emitted by a fluorophore. That is, the emitted light from an excited state can be absorbed by a molecule known as quencher. By this absorption, the intensity of fluorescence is decreased. Basically, this quencher is a heavy ion or an acceptor molecule. Now we have to discuss the applications of quencher. We can apply different concentrations of quencher to the system. At different concentrations, the absorption power of quencher is different. That is, they absorb the emitted light at different intensities. So, at a different concentration, we can observe the fluorescent intensity. That is, we can observe the difference in the fluorescent intensity. And this relation, that is the relation between the concentration of the quencher and the intensity of the fluorescent light, is described by Stern-Volmer equation. This equation can be used to detect the lifetime of fluorescence. That is, how much duration will be there for the fluorescence, or when the fluorescence end. This is a plot showing fluorescence intensity at different concentrations of quencher. You can see many bell-shaped diagrams there. The y-axis is fluorescence intensity and x-axis is wavelength. You can observe that the height of the bell-shaped curves are different. When the quencher concentration is high, the intensity of the fluorescence is low, so that the height of that curve is very less, and vice versa. This is the instrumentation of fluorescence spectroscopy. You can see a light source there. The light is passed through a excitation filter and it reaches the sample from which the fluorescent light will be emitted, which is passed through filter 2, that is the emission filter, and finally it reaches the photo detector.